All right, good evening, physics fans. Today we're working on a relatively standard linear momentum problem, which I'll try to sketch out for you. So it starts with an object at rest, and somehow that object splits into two pieces. Now, this could be an explosion, it could be a nucleus decaying into smaller pieces. But somehow or another, this object at rest splits into two pieces, each with a mass. We call them M1 and M2, and they're traveling in opposite directions. Now, the problem tells us that one mass is 1.5 times as massive as the other. So we'll take this first piece, M1, and let's just say that it has 3/2 the mass of M2. It's 1.5 times as massive. And this is completely arbitrary. We could have said mass 2 was 3/2 the mass of M1. It's a choose your own adventure. But we'll say mass 1 is equal to 3/2 mass 2. And we're asked to find the kinetic energy of each piece, the kinetic energy of M1 and M2. We are also told that the total kinetic energy after the decay or the explosion is 7,500 joules. Now, it's worth noting that this is a completely inelastic process. As you've probably learned, collisions of any type are either elastic or inelastic. In inelastic collisions and inelastic processes, kinetic energy is not conserved. Notice at the beginning there was one particle, it was at rest, there was no kinetic energy. And then it splits, it decays, it explodes, and now you have 7,500 joules of kinetic energy. So energy in this case is not being conserved. In elastic cases, energy is conserved, and inelastic energy is not conserved. But in both cases, momentum is conserved. And so for problems like this, I recommend starting at first principles. And that first principle is the conservation of momentum. Namely, that the sum of all the initial momenta is equal to the sum of all the final momenta. And I'm going to be a little bit anal, and I'm going to include the vector hat because momentum is a vector. Now, you might recall over here on the right, we're keeping track of important things. The definition of momentum is, by definition, mass times velocity. So we've got our conservation of momentum over here on the left, and initially, before the decay, before the explosion, nothing was moving, there was no momentum. And afterwards, after the event, we have two momenta. Momentum of the first particle, which is just mass of the first particle, m1, times velocity of the second particle, v1, include the vector hat for now, plus the momentum of the second particle, which is just the mass of the second particle, times its velocity. All right. Now, we're at a point where we could, these are velocity vectors, we could split this into two pieces, an x piece and a y piece. In this case, we would say, well, the initial x momentum was 0. And so then that must be equal to the first mass times, let's call it v1x, the x component of its velocity, plus the second mass, m2, times v2x, the x component of its velocity. Similarly, talking about y components, that would just be first mass times y component of its velocity, plus the second mass times the y component of its velocity. All right. Now, at this point, I'm going to make a little tangent. If you're given a problem where you have a mass and it splits off, but maybe the two trajectories aren't nice and horizontal, they're not lined up like our picture here. If they're at some arbitrary angle, let's say, like in this picture to the left, Well, your instincts might say, well, we can take this, velocity of the first particle, we can split it apart into x and y pieces, and we could, plug that into these guys. And that's a valid way to do things. But there's a nice little trick here. We can always, take this whole system. We've got this particle splitting into two pieces at some weird angle. And notice the two vectors are in line with each other. They're parallel, or more correctly, they're anti-parallel. We could take this whole system and we could rotate it. Rotate this whole system. And we could rotate it until these two vectors are lined up with the horizontal. You always have the freedom to rotate your system in any problem. Or equivalently, you can rotate your coordinate system. So the problem that we're given, I drew these horizontally. I'm saying x is horizontal, y is vertical. But there's no harm in saying, for example, let this angle be the x direction and let y be like this. So you can always rotate your coordinate system. And so even in the case where you have something that isn't horizontal, realize that this is still a one-dimensional problem. We get to define what x is. And so even if you have some weird angle going on, as long as these two vectors, the two vectors of the splitting pieces, are in line with each other, it's a one-dimensional problem. And so in this case, or even in the case drawn to the left, there is no y component to velocity. And so we can say the the y component here is 0, y component here is 0. And so we can ignore this whole line and focus just on the x component. All right, so we have m1 v1 plus m2 v2 is equal to 0. Let's solve that real quickly and say m1 v1 must then be equal to negative m2 v2. Okay. But we know up above, given in the problem, that m1 is equal to 3/2 m2. So we can say this is really just 3/2 m2 times the velocity of the first particle. That must be equal to negative m2 velocity of the second particle. And you'll notice now we have an m2 on both sides of the equation, and so we can cancel that out from both sides. And now we have an equation just in terms of velocity. And we can solve for either velocity. I am going to solve for v1 though. And we can solve for v1. v1 is just negative 2/3 of v2. And that is important. So we can circle that. Okay. Of course, the problem asked us, this particle decays, splits into two pieces. What's the kinetic energy of each piece? Well, we know each piece has a certain kinetic energy. Kinetic energy of the first piece plus kinetic energy of the second piece. Wow. And together, those have to be equal to the total kinetic energy after the decay or after the explosion, which we said is 7,500 joules. Now I'm going to remind you the definition of kinetic energy. Kinetic energy is, let's try that again. Kinetic energy is 1/2 mass times the square of velocity. Now the problem gave us some information about mass. It said one mass is 1.5 times the other mass. So it told us that mass 1 is 3.5 times mass 2. But it said nothing about velocity. Talk about kinetic energy, you need to know mass and velocity. But we used conservation of momentum, and we found that v1 was negative 2/3 of v2. Try that again. And don't let the negative sign throw you. That's just a directional thing. In the picture we drew, v2 was to the right, and so what's negative right? Negative right is left. So this just says that V1 is the opposite direction of V2, it's in the left direction, and it's 2/3 the magnitude. All right, so we've defined kinetic energy, and now we can start plugging this into our energy equation. So we know kinetic energy of the first particle is just 1/2 mass of the first particle times the square of its velocity, plus the kinetic energy of the second particle, which is just the mass of the second particle times the square of its velocity. But we can rewrite that even more, because remember, we said that M1 is just 3/2 of M2. And we said that V1 is just negative 2/3 of V2. Okay, that second term hasn't changed yet, not yet. Still 1/2 M2 V2 squared. All right. You can do a little bit of math now. The mass is still 3/2 M2. Now, negative 2/3 squared. Well, that's just positive 4/9. That's now a V2 squared. And we still got the 1/2 M2 V2 squared. All right. All right, now a little bit of mental math. 3/2 times 4/9. That's 12 up top, 3 times 4, over 18, 2 times 9. So that's 12/18. 12/18 is just 2/3. So I'm going to pull out a 2/3. We have a 2/3. And we still have the 1/2 M2 V2 squared plus 1/2 M2 V2 squared. Now, notice we have a 1/2 M2 V2 squared and a 1/2 M2 V2 squared. And so we can factor that out from both terms in the equation. So we've got a 1/2 M2 V2 squared. We factor that out. So we've got a 2/3 here. There's really a 1 here. We've got 2/3 plus 1. And notice we've been carrying through the equal sign this entire time. So this whole final term must be equal to 7,500 joules. But now look, we have everything in terms of the mass of the second particle and the velocity of the second particle. All right, so now a little bit more mental math. 1 plus 2/3, that's what, 5/3. And so what happens, I'm going to draw a little demarcation here. If we multiply both sides of this equation by 3/5, so times 3/5 on this side, times 3/5 on this side. All right, well, so this term in parentheses, this is 5/3. 5/3 times 3/5, these cancel out, and this just becomes 1. 3/5 times 7,500. Don't trust me, if you have a calculator and you want to check, you can go ahead and verify, but 3/5 of 7,500 is 4,500 joules. Again, these terms have canceled out on the left-hand side, so the left-hand side is just 1/2 M2 V2 squared. But of course, 1/2 M2 V2 squared, that's just the kinetic energy of the second particle. And so right there, we've already found the first part of our answer. Circle that. The kinetic energy of the second particle is 4,500 joules. Now, if we go back to the top left of the screen, we see kinetic energy of the first particle plus kinetic energy of the second particle is equal to 7,500 joules. But the kinetic energy of the second particle is just 4,500 joules. Just solve that. So subtract 4,500 from both sides, and what we find is that the kinetic energy of the first particle, and for completeness, we'll just write out that's equal to 1/2 mass of the first particle times the velocity squared of the first particle is equal to 7,500 minus 4,500. That's a nice even 3,000 joules. So we have a particle initially at rest. There's no kinetic energy. It decays into two pieces. The first piece has a kinetic energy of 3,000 joules. The second has a kinetic energy of 4,500 joules. And that is the solution to the problem. So just a quick recap. We restated the problem already. We know something about the mass of the two particles, how they're related. And we know that even if energy wasn't conserved during the decay process, during the explosion, that momentum was. And so we realize this is a one-dimensional problem, and we can go ahead and use conservation of momentum to find some kind of relationship between the velocities. And once we have that, we have a relationship between the mass, relationship between the velocity. Then it's just a little bit of algebra and ends with something that's plug and chug. We find the exact value of the energy, kinetic energy, for the two pieces. All right, I hope you